Okay, so let's deal with the differentiation chain rule, bits and pieces. Chain rule is a very, okay, I don't want you to think of the chain rule, okay? I want you to think of it as the outy-inny rule. On the basis that you differentiate the outside, leave the inside alone, and then you basically work your way gradually inwards, differentiating the inside bits. So the reason why the chain rule is used, or when is the chain rule used, it's used when you have a function within other functions, okay? So if I write it like this, so if I have a function and then buried within that function, I have another function. And in fact, this chain can carry on going, so I can have a function inside a function, inside a function, inside a function, etc. So for example, you might have something like the tan of 3x plus 4, like so, okay? You can see here that I have a function, tan, and then inside that function I have another function, okay? Or I might have something like this. So I might have the sine of e to the power of x squared plus, let's say, cos of x. So once again, if you look at that one, there's lots of functions going on there. Sine, that's a function. E, that's a function. X squared plus, and then another function buried within that. Right? So you've got functions buried within functions buried within functions. Whenever you see that event happening, I want you to think that's the chain rule, okay? So you've got functions buried within functions buried within functions. And if you want to differentiate these things, then you're going to have to use the chain rule, okay? It's different from the product rule or the quotient rule. Those are the only other two rules that we look at with differentiation, really. Obviously, we look at the power rule, which is just like differentiating things like x squared. But yeah, so the product rule says if you have a product of functions, you're timesing functions together. Here, you're not timesing functions together. You've got definitely functions buried within functions buried within functions, okay? Same with the quotient rule when you have division of two functions, right? Again, here we haven't got division of functions going on. Now, it might well be that in reality, in an exam-style question, I'm going to ask you to use combinations of these at the same time. So I could absolutely give you a product of functions where each of those functions have functions buried within functions, right? So you'll have to use chain rule in combination. But let's do an example to make sure we're happy. So let's actually take this second one. Let's take y is equal to the sine of e to the x squared plus cosine of x. Okay, let's first of all figure out what the different functions are, okay? So are you happy that first of all sine is the function that we're going to start with? Yeah. So if we differentiate this, so I'll write dy by dx because my variable is x. Let's start off just by differentiating sine. Let's differentiate the outside, leave the inside one alone, okay? What's derivative of sine? Cosine. Good, cosine. Everything else I leave alone, don't do anything else at this stage. So the inside function, I don't touch at all. Okay? But then I need to go back and differentiate the inside function. Okay? So if I differentiate e, that's my next function, I'm working my way inwards. I'm going to multiply by, what's the derivative of e? E to the power of something? E. Good, it's just e to the power of something. So I'm just going to leave e, leave that alone. X squared plus cosine of x. Now I can work my way inwards again to the next function, so the last function, is the power, this one up here. So if I differentiate that, the x squared plus cosine of x, I'm going to put it all in a bracket because I want to differentiate it all. What's the derivative of x squared?
2x.
2x. What's the derivative of cosine of x?
Sine. Minus sine.
Good. Minus sine of x. And there you go.
So, it's finished.
Yes.
That's it.
That is it. Literally just work your way inwards, right? Now, you could try and tidy this up. I wouldn't. Leave it like this,
Okay.
right?
Can you show us that you've done the process correctly if you did that thing?
Yes, exactly, yeah.
That we understand that you have to take it step by step.
Yes, yeah. Exactly, I mean, literally all I'm doing, I've run out of colours, so I've only got two colours really to play with. But the first bit is just differentiating the sine function, okay? The next bit is just differentiating the e function. And the last bit is differentiating that last function. So I guess I'll underline that. Okay, so literally outside, inwards. Of course, there's nothing stopping you doing the inside outwards. That's the same thing because it's all multiplied, right? Doesn't matter what order you go. I personally prefer to do the outside inwards. I find it easier to keep my head around, but it's up to you. I can give you another example just to make sure we're happy. Something like y is equal to, let's try the tan of 3x. In fact, I'll make it a little bit more interesting. Sorry?
What is 0 root?
That's exactly my question.
Really?
So the natural log, let's make it a natural log of 3x plus 4 rather than just 3x plus 4 because I'm feeling that. So come on then, so dy by dx. So the first question is, yeah, absolutely. What is the derivative of tan? So if I just take a function, I'll write it over here, I guess, okay? So if I take the tan, in this case I'm just going to write it as tan of x, because of course you realise that whatever's inside is going to stay the same. So if we just deal with tan of something, tan of x, and if I want to differentiate this. Okay. One way that you can think about it, I mean, it is a standard result, so you can absolutely just use that standard result. You don't have to do this derivation if it was an exam style question. But one thing I'm going to say, d dx. Tan of x, if I can't differentiate it at the moment, let's think about tan of x as a composite of functions which I can differentiate. What do you reckon?
Sine and cos.
Sine divided by cosine.
Excellent, yeah, well done. So yeah, because tan, you remember that identity, tan of x is just literally the same as sine of x divided by cosine of x, I know how to differentiate each of those, right? So, if you think about it, what am I doing with these two functions, sine of x and cos of x? It's literally what's going on here. So sine of x, cos of x, what am I doing to them?
Dividing.
Dividing, which means I'm going to be using the
Cro.
quotient rule. Perfect, yeah? So division, another word for that is a quotient. Quotient of two functions, division of two functions. So I'm going to have to use the quotient rule here. So the quotient rule, remember, goes, if that's u, and that's v, it's in the formula sheet, differentiate u times it by v. Minus differentiate v times it by u, divide by v squared. Okay, so my numerator is always u, my denominator is always v. Let's see if we can do that in our head. So, derivative of u first. What's derivative of sine?
Cosine.
Cosine. Times it by v. Minus, do it the other way around, what's derivative of cos?
Minus sine.
Yep, minus sine, so change that to a positive. And times it by u. Good, so you're seeing that already. Divided by v squared, so that's going to be cos squared, right? Thus, cos squared, because that's cos times cos, plus sine squared, because that's sine times sine. Cos squared plus sine squared is?
1.
1, perfect. So this just becomes 1 over cos squared of x, or if you prefer, you can write that as sec squared of x. If you want to leave it as 1 over cos squared, that's fine. It's just basically there are reciprocal trig functions that exist, right? Which is basically you take the third letter of that and it becomes the beginning letter of that, is the way which it works. So 1 over sine becomes cosec, 1 over cos becomes sec, and 1 over tan becomes cot. Okay, so I'll write that in the top right hand corner in case you were interested. In fact, I'll write it over here. So okay, I said 1 over sine is equal to cosec, 1 over cos is equal to sec, that's the one which you've got there, and 1 over tan is equal to cot. The reason being is because these reciprocal functions come up quite a lot. It just makes sense to just give them another name rather than seeing 1 overs all the time. Yeah. But yeah, the way which I remember this is that the third letter of each of these reciprocal functions is the beginning letter of the original function. Okay, so it's a nice little way to remember them. But either way, 1 over cos squared, sec squared is fine. Coming back over here then, so you can just quote that result. Okay, you don't have to do this every single time now. But if you come back over here, if I say what's the derivative of tan, what would you say?
1 divided by cos squared.
Okay, so you're going for that one? That's fine. I'll write sec squared if that's okay. Yep. So I'm going to write sec squared of, leave the original function, or leave the inside function alone. So natural log of 3x plus 4. Okay, so now I need to times by, work my way inwards. I guess the next function I'm going to see, natural log. What's the derivative of a natural log function? Good, exactly. It's a 1 over function. Of course, leave the original function alone. So it's a 1 over inside function left alone. Then I'm going to times it by, work my way inwards again. What's the derivative of 3x plus 4?
3.
Just 3. There you go. So you can see again, derivative of tan is the sec squared bit. Derivative of the natural log is that bit. Derivative of the 3x plus 4, that bit. Make sense?
Yeah.
Excellent. Okay.